All right, today we're going to walk through exactly how convolutional neural networks work. In order to get started, we kind of need to ask the question, well, what are convolutional neural networks? In deep learning, a CNN or ConvNet is a class of artificial neural network most commonly applied to analyze visual imagery. Two main downstream tasks include image classification and semantic segmentation, and then CNNs are also used to encode images by compressing the information into different feature spaces. There are two main components to every convolutional neural network, regardless of the downstream task. Different downstream tasks require different end transformations, but at their core, each CNN has a few things in common: convolutional layers and pooling layers. Convolutional layers are responsible for generating the filters or channels of intermediate feature spaces. When creating convolutional layers in modern deep learning APIs, one of the input parameters is the number of filters. When specifying the number of filters, you are specifying the number of different learnable kernels you want to be generated for that hidden layer. So each convolutional layer has its own set of learnable kernels, a set stride, which is the gate in which the kernel is passed across the input, and a specified padding. The standard convolutional operation pools the input feature spatially. This is often mitigated by adding what is called zero padding to ensure the output dimension stays the same as the input dimension. The spatial pooling or compression of the input feature space is generally handled by the pooling layers. Regardless of how it is accomplished, the general flow of the network is to generate intermediate feature spaces that are gradually spatially compressed before being transformed for some downstream task. The goal is to generate a model that learns a hierarchy of kernels to generate a feature space that optimally solves the specified task. So let's go ahead and take a look at one of the most common use cases of a convolutional neural network. This one is designed for image classification. If you direct your attention to the left side of the screen, we can see the input is the image of a deer. As we traverse through the network, we see there are convolutional steps followed by pooling steps. If we look at the first block of blue features after the input image, we can see there's 4 channels, or it's 4 channels deep, and these are what we would call the filters. Each one of those channels has its own corresponding learnable kernel. Those input features are then sent through a pooling operation, which compresses the information spatially before being sent to another convolutional layer. At each convolutional step, we see that the feature space deepens. That is, the number of filters increases, generating more kernels to learn unique features before being passed, in this case, to some densely connected layers for the downstream classification task. Here is another view looking at the same concept, where the convolutional layers are used to deepen the number of features and the pooling layers are used to compress the input information spatially to create a model that can effectively encode images in such a way that the features generated by it are generalizable and optimized for downstream tasks. So you might be asking, what does this look like on a lower level? You might understand the idea, but what are the fine details? Well, here are some examples of those kernels we talked about. These are examples of traditional kernels that have long been used in image processing to find things like horizontal and vertical lines, or different types of lower level features. These have been hand engineered by humans and are extremely useful. The main idea behind convolutional neural networks is to take this traditional image processing idea where we generate useful kernels that find useful features in our data. And what we're trying to do is automate that. Automate the search for the most optimal kernels to be learned for our downstream task. So luckily, when it comes to optimizing any type of function, all we need to do is ensure it's represented in such a way that it's differentiable with respect to our target variables, and then we can optimize it through gradient descent. And there we have a convolutional neural network, a model that learns the best kernels for generating the best features for some downstream task by following the instructions given to it by the training data. If your training data is representative of the target problem and our loss function accurately represents the problem, then the model can incrementally, through millions of trial and error experiments, change and learn the best solution. Let's take a look at the first building block, the convolutional operation. For each of the specified filters, a kernel will be generated. The most common kernel dimensions are 3x3, 5x5, and 7x7. Here we have a 3x3 kernel and an image matrix. To generate the output feature, the kernel is passed over the image at a set stride. In this example, the stride of the operation is 1. At each step, an element-wise multiplication is performed between the kernel and the image, and then the aggregate sum of the resulting matrix generates a single output value. This is what we call the convolutional step. That output value is then sent through a nonlinear activation function to get the final value. That's what we call the detection step. The most common activation function is ReLU, or what's called rectified linear unit, which sets all negative values to 0 and then leaves any positive values as they are. It's a nonlinear activation function that's very, very close to a linear function. This is done until the kernel has passed over the entire input feature, generating the entire output feature. Let's dive even deeper. Let's take a look at what is happening in one step of the operation. So the input feature, the majority of the time, is not just a single channel. Usually there are multiple channels underneath. For example, a normal image has 3 input channels, which are the red, green, and blue. Also, as we just saw, the deeper the model gets, the more filters or channels there are. So you might ask, how is each kernel applied to all of the underlying channels of data? Here we see the 3 underlying channels are expanded. The kernel is then broadcasted to each channel, and then each channel is multiplied by the kernel in parallel. Then to generate the output value, again, we take the element-wise sum of the multiplied features, and then we take the aggregate sum and pass it through the ReLU activation function. This generates one output channel for that kernel. So to generate multiple channels for this intermediate feature, we need to create multiple different kernels and then repeat this operation for all of them. Let's take a look at some of the features generated at some of the levels of the network. The features on the left are features learned in the first few convolutional layers, and as we work to the right, we start to see the features learned as we go deeper into the model. We can see edges, parts of faces, and then entire faces. Here we can see the same concept, but these are features learned from a different data set. Again, as we move deeper into the network, we see that more and more complex and abstract features are learned. These features are more specific to the data set on which the model is being trained. So essentially, we're able to, in the first starting convolutional layers, learn things like edges, as it's looking at a very small spatial subset of the input image. And then as it is pooled, the kernel is able to look at larger subsets relative to the input image as the input feature space has been compressed, and it's able to learn and pick up on different patterns and more abstract patterns that are more relevant to the actual target training data set. So why does this happen? This happens because of the spatial pooling that is applied after each convolution. Here we have a 2x2 max pooling layer with a stride of 2. As we watch, the kernel is passed over the input and the maximum value in the subset is then taken to generate the output value. Why is this important? The max pooling operation introduces invariance, which is an infinitely strong prior. If applied to an input feature, max pooling forces the model to learn a function that is invariant to small translations, which significantly improves the statistical power of the model. Even more, if the max pooling operation is applied to separately parameterized convolutional outputs, the model learns which features to be invariant to. Aside from adding invariance to the model, the pooling layer also effectively compresses the information as it's fed deeper into the network. This compression allows the same 3x3 kernel to essentially encompass more spatial information in each pass. Here we can see, as the information is compressed, the kernel takes a wider look at things relative to the original input feature space. This allows it to learn more complex features and to see whole objects like faces or more abstract features. This is how the model builds its hierarchy of features. To bring it all together, let's revisit an example showcasing the same type of CNN that's designed for image classification. We can see that the input feature is pooled spatially while the number of filters or channels is increased as we go deeper into the model. Then at the end of the convolutional operations, the final features are used for some downstream task. In this instance, they are sent to some densely connected layers before being sent to an output for a softmax prediction over multiple possible classes. The power of convnets lies in their computational efficiency and the priors that have been encoded into them through their operations. The ConvNet is similar to a fully connected network, except the ConvNet has infinitely strong priors encoded over its weights or its kernels. The priors are the weights of one hidden unit must be similar to its neighboring units, just shifted. This comes from the weight sharing in the convolutional operation and the passing of the same kernel across the entire input feature space. This forces the model to learn a function that contains only local interactions and is equivariant to translation. The pooling operation also introduces the prior that each unit should be invariant to small translations. So the computational efficiency gained and the memory usage reduction is massive from incorporating these priors. It prevents having to parameterize every pixel in the image. Instead, we only need to parameterize the weight kernels and store only those weight kernels throughout the entire training of the model. So there you have it, the basics of what's going on inside of a convolutional neural network. And I hope you were able to learn something, take something away from it. If you kind of like these different types of deep explanations into some of these data science or machine learning type concepts, let me know. Leave a comment in the description talking about some other possible ideas or things you would like me to cover. So again, I hope you enjoyed, and I'll see you in the next one.